That was a wonderful introduction. Thank you. I thought I should turn up to this talk. Hello, everybody. Hello. Hello at the back. Hello at the front.
The machine is telling you hello. You unfortunately have to say got it if you are to proceed.
And hello, everyone on the internet.
Like that.
Could I have a reaction? People on the internet, could you give me a thumbs up or whatever reaction? Perfect. Thank you, Vikraman. More people, please. Jack, Mohammed, Jan, Greg. Bring it on. Good. Thank you. So, Najib, could you please be officer in charge of alerting me if there's questions from the internet?
Sure, yes.
Thank you. Okay, so it's a pleasure to be here. Thank you for inviting me, and John, thank you again for the wonderful talk. It's the best lead-in ever.
Jamie, would you be kind enough to full screen yourself? Or
yeah. How do I full
F5 maybe?
F5.
Control L.
Control L.
There's an arrow at the top right. It goes like a diagonal arrow. Try that.
Nice.
Wonderful. Thank you.
Now you want to do something with the top bit.
I think you just move that to one side.
I'm going to leave it. It's not going to make any difference.
Okay.
Yeah, so thank you. And following on from John's talk, I'm going to survey nominal algebra. Nominal techniques, the original application was to inductive syntax with binding. I won't talk about that today, just because. I'll talk about nominal axiomatizations of substitution and first order logic. And then I'll describe why that was actually the easy bit, and I'll describe what the hard bit actually turned out to be. So part of the point of this talk is that the stuff that gets attention, and certainly the stuff that attracted my eyes at first, was not actually the difficult stuff. The hard stuff turned out to be not at all what I expected. So this is, in a sense, it reflects the journey that I've made. And this talk will be opinionated. So I will express opinion. And I mean this in a positive way. I'm reflecting on things that didn't go as well as I'd hoped and why. And you're welcome to heed this history, and you're very welcome to ask questions and pass comment. Hands up if that's okay, and I can move to the next slide, please.
Got it.
Fabulous, thank you. So let's do some background stuff. Stop me if you get lost, that's fine. So let's fix a countable set of atoms. Okay, A, B, C, X, Y, Z, whatever. And a permutation set is just a set with a group action by the permutations of atoms. Fine so far? If you're lost now, I need to know so I can adjust, right? So, and I'll say that a function is equivariant when it commutes with the permutation action. So a canonical example of this would be, say, the identity function. So if I apply pi and then do nothing, that's the same as doing nothing and applying pi. But pairing is also equivariant. If I take a pair of things and permute in that pair, well, by definition, permutation acts pointwise. So of course, that will be equivariant. Make sense? And the same thing for predicates. These are basically the same thing, just written from a different point of view, because you can turn a function into a predicate and a predicate into a function. So equivariance is the idea that permutations always distribute. I'll say that again. Permutations always distribute. It sounds simple, but I've worked with enough people to know it takes a while for that to really sink in. So I'll say it again. Whatever it is, permutations will distribute through it. So equality is equivariant. Well, but the catch is when you push the permutation through, you have to push it through all the parameters. So I once got a paper nearly rejected because the referee said, Gabbay claims that permutations permute through everything, but clearly x is not equal to y if and only if pi of x is equal to y. Yes, but x is equal to y if and only if pi of x is equal to pi of y. So long as you can collect all of the parameters, then you'll be equivariant. There's actually, I learned only recently, there's a principle of data invariance in programming, which says the same thing, right? If you have an underlying set and you permute, then any structures you built on top of that will just not notice.
Sorry, Jimmy, parameters of what? What are the parameters?
That's a great question. So in my paper, Equivariance ZFA, first I build the language of ZFA sets.
Yeah.
And it's the parameters in any predicate that you can write in that language.
Okay.
In practice, this is perceived by the working mathematician as I have a formula on the piece of paper. So you check all of the things, all of the dependencies that went into creating that. Those are the parameters.
So in this case, our x and y here are ranging over these predicates?
In the equality?
Yes.
No, so this, if you're comfortable viewing that as a ZFA predicate, then that's ZFA equality. But x and y can be elements of an arbitrary permutation set.
Okay.
Which comes with an equality and bang. Yeah? Thank you. Just out of interest, hands up who understood that little exchange. Hands up who didn't understand it. Okay, it's cool, doesn't matter. Okay. Point is, this pi, Swaraj, this pi thing here, it's a bijection. So obviously, if something's a bijection, f of x equals f of y, and if and only if x equals y.
Right, yeah.
But this permutation thing, it's not any old f, it's a specific thing, and it always distributes. Okay, one little bit more. Let's take a finite set of atoms and let's make this concrete. So I'll have two atoms, A and B. That's my S. And I'll write fix S for the set of permutations that fix every element in S. So, for example, the identity permutation is in fix AB. Why? Because A is equal to A and B is equal to B. If we take this swap in, swap A and B, which takes swaps A to B and B to A. Oh, notation crash here. I'm going to have to rename my atoms to A primed and B primed in S there to avoid clash, right? So this is in fix S if and only if A and B are not in S. And just there's one thing that can go wrong here pedagogically. Swap A and B is not in fix of the pair, the unordered pair AB, because swap A and B apply to A is equal to B. What can go wrong is readers think, oh yeah, of course this isn't fix this, because if we swap A and B in this unordered pair, then we get that unordered pair. That's a perfectly legitimate thing, but that's not what fix does. It's point-wise. Hands up if that makes sense, please. Philippe, you.
No, it does. It does.
Okay, gravity was just getting the better view of you now.
Question gets the better of me though, Jamie.
Yeah.
Given your specimen example of A comma B, and also the examples on the slide, do you have to take special care over the case A equals B?
So I will follow a permutative convention that if I write A and B, unless stated otherwise, I assume they're distinct.
Good.
But if it becomes an issue, then I would make it clear.
Good, thanks.
Thank you for the question. Go ahead.
Do you assume they're distinct, or do you take them to be literal A, B in your set of atoms, say 0 and 1? It doesn't matter.
So it doesn't matter, but I'll just tell you it will become clear in the rest of the talk that I actually believe in the set of atoms. So well, there are people who are religious and there are people who actually believe in God. And sometimes it can be quite startling. There are people who aren't religious and actually believe in God. These are two orthogonal axes, right? So I actually believe in that set of atoms. And this talk is an argument that you should too. So it's not that A is secretly being zero. You know, when it comes off work, it takes off its dress and you discover that it's actually the number zero. No, A is actually A, whatever A is.
It's a literal A. It's a literal atom A. Rather than a meta variable for an atom.
I understand your question and I'm not going to answer it.
Sorry.
No, it's fine. That's fine.
Thanks.
Well, okay, I will answer it. There's two ways of looking. Either I actually believe that there is an atom A,
Yeah.
or A and B here are meta variables ranging over distinct elements.
Yep.
Either reading will be fine for this talk.
But you're not going to tell me which one you meant.
I don't really care.
Okay, thanks.
Thank you. Great question. Sophisticated question. Okay, and now we are going to need support. So this is it. Okay, this is as bad as it's going to get, which is, to be fair, not very bad. So we'll say that a finite set of atoms S supports X when every permutation that fixes the atoms in S pointwise will also fix X. So fixing X just means that pi acting on X is equal to X. Fixing S pointwise doesn't mean pi S equals S, it means pi A equals A for every atom. Yeah. And then there's some lemmas. So S supports the atom A if and only if A is in S, pretty much by definition, because if A is not in S, then we can take a pi to move A, so that's it. And S supports a finite set of atoms for similar reasons, if and only if that finite set of atoms is a subset of S. This is a tricky one. People have trouble with it. So I will draw you a picture. So I reached out into the Platonic universe and I pulled out the set of atoms. Here it is. And I'm going to take all the atoms except for AB. So this is atoms minus AB. Now let's think of a permutation. If the permutation moves A or B, then it could move this whole to be somewhere else. But if the permutation fixes A and B, then yes, it might send C to D, but we'll never notice because they're both just in this mass of atoms, right? Make sense? Any questions on that? It's like a river. A river is under constant translational motion, but it looks like a river to you because for every molecule of water, it's just being shifted along, the shape remains the same. What you would notice is a splash. And in the same way, so long as pi doesn't move A and B, it will fix this mass of other atoms. Kieran.
Your support operator is acting on atoms as well as sets of atoms. Is this all fine? Because this necessarily means that your atoms have to be distinct from your sets. So is this a reason why you have to use some ZFA type stuff? Or you get away with, you could build all of this stuff that you've presented so far in just pure ZF for France. Is this the beginning of why we need these things to be completely different?
So I didn't understand all of that question. I can confirm that I'm secretly working in ZFA sets. Yeah. So atoms and sets are just elements, yeah. But you can type it with no trouble at all. Atoms are a permutation set where pi acts on the atoms by function application. So it's not a problem to define a support function on the type, the permutation set of atoms. Does that answer your question? James?
Well, I was going to interpolate between Kieran's question and your answer, because this slide has no definition of a set supporting a set, only a set supporting an element.
Oh, yeah, so hang on. No. X is a permutation set. I'll come, do I come to power sets? I don't even remember if I come to power sets. Hands up if you want to see the definition of the permutation on power sets. Marco put his hand up. That's good enough for me. So it is true that if X dot is a permutation set, then the standard power set of X dot is a permutation set with a pointwise action. Pi acting on X is equal to pi acting on little x for the little x in X. So that's an automagical way of making, if you have a small permutation set, you can get a bigger one. And everyone knows that once you have a big set, you can cut it down, shave it down to the shape you want. But that's not relevant to this talk. I'll write A fresh for X when A is finitely supported by some set that A is not in. And if you think about what that means, it's very much, to give you some intuition, you know what free variables of the term are, and you know how permutations act on the term just by acting on the free variables, then the support will correspond to the free variables of that term. The support is measuring the asymmetry of the element. So if A fresh for X means that whatever X is, a term, a set, it doesn't matter. X is symmetric under moving A around most other atoms. Hands up if I can carry on, please. Okay, thank you. So nominal sets are just permutation sets where everything has finite support, which is a fancy way of saying that if I give you something, you know that it only has finite asymmetry up to permuting names. That's all it says. I once read some advice to young parents, and there was a bulleted list, and the one that I remember was any mess can be cleared up. Any mess. So no matter how much entropy a small child can generate, no matter how much asymmetry they can introduce, it's finite. You can get back to tidiness. And in a similar way, what this is excluding is things like every other atom, right? That's not finitely symmetric, because for any finite bit of it, there's always one atom that's in it and one atom that's not in it, just to give an example. Okay, well, that's it. That's it for the theory. So let me show you something, a wee trick. Let's assume an X, which is a permutation set. In fact, it's a nominal set. And I'll just assume what I'll call a substitution function, which is a map from X, from tuples, X, A, X primed, X. And I'll write it in the usual way, Z with A substituted for X. But note, this is an abstract function. It's not an actual substitution on syntax. It's a thing that I'm calling a substitution. And what gives me the right to call this thing a substitution? Because it satisfies these three axioms. If A is fresh for Z, then Z with A replaced by X is equal to Z. Hands up if that makes sense intuitively. Hands up if you've got no effing idea what I'm talking about. If B is fresh for Z, then we can alpha rename. Z with A goes to X should be equal to swap B and A and Z with B goes to X. And this last one is often known as the substitution lemma in the lambda calculus. This isn't a lemma, it's an axiom. This axiomatizes substitution. We're mathematicians, we have to prove this. So there is a paper, which is, hyperlinks don't work on this, but it's here. So what we do is we show that these axioms are, I think, what's called omega, they're sound and omega complete, which means that if you take an arbitrary syntactic model of terms, and interpret this as actual substitution on those terms, then this is precisely what real substitution satisfies over all possible syntactic models. That's omega completeness. So when I call this an axiomatization of substitution, I really mean it. This is an axiomatization of what substitution does.
So in your ZFA world, this is just like a function symbol, like a ternary function symbol that's been axiomatized in your logic, or do you actually define this operator?
Well, so this is an algebraic, so algebra is a logic of equality. So what is an algebra? It has a carrier set and operations on it satisfying certain axioms. So this can be defined on any permutation set. Where you get your permutation sets from is up to you. You could go into ZFA and build a set with a permutation action there. I personally would get it.
You can do it anywhere. Right?
Exactly.
This structure exists regardless of what you're working in.
Yes, thank you.
So yeah, maybe it's very related. You think that I have a substitution structure on a permutation set, or every permutation set admits a substitution structure that's can be given as a meta?
In order to play this game, you, for example, would have to come to me with a permutation set and a function of that arity satisfying those axioms. And that is a substitution, I call it a substitution algebra.
So for example, the one that completely ignores the substitution and keeps sets the same would satisfy this and would be fine, right? Oh, that's not true. The second one will get broken.
Yes, if that is true, the second one will be broken unless you're smart and you let Z be itself. If you let this in every element be a set with, if you let the permutation action also be trivial.
Yeah, that happens.
So you could give me the natural numbers and say, hey, this is a substitution algebra, and that's true in the trivial sense. That there's no atoms in it. So yes, if you substitute intuitively, that actually makes sense. It's not a pathological example, it's what you'd expect.
So you're right in that in order to play this game, you need to give the permutation set X, but you also need to give some set A for your atoms, or you just have to assume that your logic just has some atoms out there, right? And surely that set of atoms needs to satisfy certain properties as well as these three axioms that are here.
So I refer to my previous comment that I actually do believe in the set of atoms.
Yeah.
So the atoms are, it's always going to be the same set throughout this talk. I don't need to provide the atoms again because I've already told you what it is. However, having said that, it's legitimate to say, well, what is it about atoms that makes them nominal atoms? And that is indeed what this talk is about. And the punchline will be that atoms are precisely the things for which you get an equivariant permutation action.
Very good. Excellent.
My pleasure. Any other questions? Okay, so just to sum up this slide, hands up if you did a course with groups, rings, or fields in the title in uni. Classic, right? So a group is a carrier set with a binary operation, blah, blah, blah. A substitution set is a carrier set with a ternary operation, blah, blah, blah. This is an algebra. I'm less concerned about the precise axioms of the fact that in a nominal universe, we can write this and it makes sense. Now, a question you could ask is, Jamie, you claim this is an algebra, but what is an algebra? And I might say, well, it's a logic of equality and you have a syntax. And then you might say, what is the syntax? And I tell you that. And you say, great, but look, that thing, that's a side condition. These aren't equalities, these are Horn clauses. I went to the trouble, and it was quite a bit of trouble, of proving that the definitions which I've not given you, but for nominal algebra, there is an HSP theorem for this thing. The HSP theorem is a very, very characteristic property of universal algebra. Horn clause logic does not have an HSP theorem. So the fact that nominal algebra has an HSP theorem is a way of formally stating that this thing really is an algebraic framework.
It doesn't matter what HSP expands to.
Homomorphism subalgebra product. And this really matters because I had a lot of trouble getting nominal algebra published because people got very confused about these side conditions. They have a very special status and it's easy to get confused about them, but it does work. Okay. Yes, sorry.
You've got fields in that list. You're trying to say something about fields aren't normally considered algebra in the sense you're outlining.
Well, in that case, I made a mistake. I thought they were.
Because they have you have to say if something is not zero, then it has an inverse.
I will delete that word.
Okay.
Thank you.
Modules, algebras, or rings or semi-rings. You said that already.
I still rings, semi-rings. Yeah, so that
I think it's good because it highlights, a side condition that cannot be removed in the same way.
Yes. Well, I thought perhaps you were going to say, oh, you can also do something for fields, so I can view it as traditional algebra in an exotic setting, which is what you're doing for nominal.
I actually never even considered that, so thank you. I doubt it'll work, but if it does, it would be really cool.
We meant vector spaces, but not fields.
I'm just going to move on.
Okay.
Let's do first order logic. As you have, ladies and gentlemen, as you have never seen it before. I still get a thrill. I really do out of this. So, hands up if you're familiar with Boolean algebras, right? Standard stuff. So let's assume we have a Boolean algebra. So it's a permutation set with conjunction, negation, and bot. And as is standard, I see yes, okay. Let's write v less than or equal to v prime for v and v prime equals v. Then this axiomatizes universal quantification. So if A is fresh for v, then for all AV equals v. The second axiom says that it's a binder. And the third axiom is just for all elimination. For all AV implies. That's it. Slogan is for equals for all plus for all. But this for all is a nominal algebra theory. I'll just carry on until somebody asks a question or interrupts. You could then ask, well, you say this is for. Prove it, right? So yes, we can build a universe of models of this thing and prove soundness and completeness. But we can do much, much more than that. We can build notions of ultrafilter, just like we do for Boolean algebras, and then prove a stone-style representation. So there's a full stone duality on models of this thing. So when I say that this is full, I mean this is to full as Boolean algebras are to Boolean logic in a really strong sense. Thus, we have extended our algebraic account from algebras without binding to algebras with binding. And I'll just mention, there's a paper where we do the same thing for the lambda calculus. This paper is 80 pages long, and after that I swore I'd never write another long journal paper again. My current journal paper is pushing 100, so I think this is a personality defect. I can't help myself. Yes.
The axioms are, I might just be being slow. Are they the obvious axioms one would write for? Like, is it easy to write the axioms for the existential quantifier? Well,
Yes, because you just use the De Morgan dual. So it literally.
Oh yeah, in this case, yeah.
In this case, but obviously you could do Heiting algebras, for example, and then for all would not be a De Morgan dual of exist, but I haven't tried that, but I would expect it to just work. You're looking forward for.
I was just thinking, there's a split in first order logic whether empty models should count, and I think your system is the non-empty models version, and I was just wondering if you could do the empty models version too.
Again, a wonderful question. Would you mind emailing me these questions so I don't forget? Thank you. That might even be discussed in the paper, I don't recall. Hands up if I can move on.
No, sorry, that was a question, Hans. Sanderson could be with respect to what? The proof system of first order logic, or with respect to a structure that's like a model theory? Then it's model theory in set theory, or is it model theory in nominal sets?
It will be the paper would be model theory in nominal sets.
No, it's not necessarily the same as model theory. So you have the model theory of these things in nominal sets, but you want to have set theoretic models of first order logic. So those structures.
If you can interpret the nominal set theory stuff in GLZF, then it's fine, right?
And you can.
You can, yeah.
Yes, that's not a problem at all. Every nominal set is already an ordinary set. I don't remember precisely, but one thing I will note is that the standard syntactic model of syntax up to derivability is automagically nominal.
I see. Right, so things kind of live there already.
Yes, they do. They live naturally there. All you have to remember to do is to use the set of atoms for your variable symbols. Okay, so why is this not better known? Well, one reason is that I suck. Right? I'm no good at publicizing myself. That's just me. Also, it's not fashionable. Categories, certainly when I started in this, categories are new and shiny. They're what people expect to see. Universal algebra is old and tired. And I've discovered, I was delighted about the universal algebra. I was delighted to build the stone duality result, but nobody cared. Although I personally rate it as amongst my strongest work. And I live in hope that the pendulum will swing back and people might get interested in this. But there's another reason. Am I doing okay for the pacing? People are shifting around. Is it too hot in here? No, it's fine. Okay. There's another reason. This is not actually the hard part. Now, to be clear, proving duality results is bloody difficult, but it's positively easy compared to what I'm going to show you next. The core difficulty is embedded in the phrase permutation set. So let's go right back to basics. The canonical motivation for all of this. So I'd done a maths degree in Cambridge, and then Andrew Pitt sat me down in his office, and he didn't quite put it this way, but he kind of said, let me show you some real problems, Jamie. And it was like sci-fi. I'd never seen anything like this in my life. We want to reconcile induction with binding. So let's consider this is just syntax, and we want to define substitution. So forget about the algebras for now. I just wanted to show you what you can do. We just want to push this substitution through this binder, but unfortunately, S contains A free. Hands up if you've seen this before. So we rename, but how? So one approach is just to create another substitution here. So we have one substitution, and now we have two. And this is awful and wrong. And you know what? I want you to go there, so you'll suffer. Okay, if you don't listen to me, then please stick your finger in this particular electricity socket. And if you survive, send me a postcard. And Fiore, Plotkin, and Turing would have used a name for name substitution. John, I think you were bang on for the money in your summary of the difference between the two ideas. So thank you for that. It means a lot to me that you actually got that right. It really does. So they do this, and notice I've used angle brackets here. So this has a different status. Nominal techniques would use a permutation, which, James, amounts to the same thing extensionally, but has a different background theory. So if A prime is fresh, then swap A and A in phi has the effect of send A to A prime because there's no A prime to send back. But whatever you use, and it doesn't matter.
I don't think it amounts to the same. I mean, it does in this particular instance. But
In this case, I'm not claiming equivalence. But they're close enough for this slide to make this point here. That's where I want to get to. Now, I didn't mean to claim equivalence. Whatever should be a finding. Whatever this is not immediately a subterm of full A phi. That dash is a typo, I'll just rub it out. So the central question we're asking is, how can we do induction when in the presence of these renamings that are provoked by alpha equivalence? How can we reconcile a need to change our minds about the name of a bound variable? How can we reconcile that with induction?
This is a bit unfair to the Plotkin-Curie story, right? Because the way they set things up is by the time you get to call the induction hypothesis, it already is stable with respect to renaming, and so you get access to the induction hypothesis in the.
Yeah, but you're jumping ahead. That is their solution.
Yes,
but it is a solution to a problem. And
okay, you're trying to show that problem.
Yeah, I'm just describing.
Yeah, thanks.
Thank you, Warren. So let's just quickly axiomatize abstraction. It's just alpha equivalence, right? If B is fresh for X, then abstract A in X is equivalent to abstract B and swap B. And then we can build an abstraction type by quotienting pairs by alpha equivalence. I don't know about you, but I'm feeling quite hot in this environment. So if your brain's switched off, this is nothing more fancy than going from lambda AA to lambda A primed A primed. That's all it's doing. But because we're in permutation sets, we can be more general. It's lambda A T, or lambda A X, for X is just an arbitrary element of the permutation set. That's all. I will mention that Atom's abstraction, encouragingly, has excellent properties. It commutes with sum and product and also function space. And one of the happiest moments in my PhD was when I showed this isomorphism to Andrew, and he told me, "Dear boy, go home and check your working. That can't possibly be true." I felt like $1 million when I said, actually, no, it does work, surely. So such moments of joy.
No, Jamie, I'm struggling to read the first line. I don't know even how to read it.
This one?
Sorry, the first mathematical line. What's written there? What is the status of what's happening there? Maybe it's obvious to someone else.
I can maybe. So you have a term X, and you abstract a variable A from it. It's the same thing as you rename A into B and then abstract B. Given that B is fresh next.
So again, I'll interpolate with a different question, which is, to what extent does that define tilde alpha for some abstract symbol, box AX? And to what extent can that be understood as defining the abstraction operator? That just seems to define alpha conversion.
It is deliberately, that's what it's defining. So that line as written is a definition that can be of a relation tilde alpha that can be applied for any nominal set. We can play this game. You give me a nominal set. With your permission, I'll call it O.
Yes, makes sense.
Okay? So O for O hat. And I will form atoms cross O, which is also a nominal set. And I'll define a relation on atoms cross O, which is this tilde alpha thing. Oh, yes, of course, sorry. I'm writing the pairs as...
yes.
Okay.
And you close it under, was it already an equivalence?
It is already an equivalence.
So these square bracket A or square bracket X, these are just pairs.
I made an error in my notation, which is confusing. I apologize.
Okay, everything's easy now.
Thank you. Thank you. So
You have now answered my original question. Thank you.
okay, I see. Yes. So my mistake, just out of familiarity with the material, I quotiented before I defined the relation. That's all. So technically, square brackets AX should be the equivalence class of the pair AX. But that line is wrong. I should have just written pairs in the top line.
Okay. Yeah.
Okay, good. Thank you.
And then we're quotienting to get the equivalence classes of all of those pairs that are alpha equivalent.
Yes.
Very good. Okay.
Thank you. Would it be too much to ask you to, in your email, slide 11 pairs? Thank you. Let's just got a round of applause. Thank you. Okay, yeah, and the fields as well. That was another thing I need to scrub. Okay, so can I carry on? Yeah, sorry about that. So yeah, we can build lambda terms, and we think we've made progress, right? But this just squeezes the problem somewhere else. Because if we want to define functions out of lambda, well, we just do the standard thing. We need to, in order to define a capital F from lambda terms to some other nominal set Y, we need to say what to do on atoms, on applications, and on abstractions. Standard stuff, right? But to define a function out of an abstraction set, we have to define a function out of this thing, because this is a quotient of that. And we have to prove that this function respects alpha equivalence. This is all completely standard, right? And this proof is actually an equivariance argument. Respecting alpha equivalence is literally saying that if pi doesn't interfere with any parameters we might have, this is just background stuff we needed to define F, please ignore it, it's fine. Then pi should commute with F prime. This is literally, if you unpack what it is to respect alpha equivalence, it's a distribution property for permutations, which is fine. But in order to prove this property naively, we'd need to induct on X. And that is the killer point, because we're already inducting on X. Because I said, suppose we want to define a function by induction. So let me just go back. So the problem I raised here is that phi with A renamed to A primed is not a subterm of for all A phi. And I said here that this thing, when we introduce another substitution, is like sticking your fingers in live electricity. It's instant disaster. But actually, we're in the same position here, because we had one induction and now we have two. Marco.
But wait, didn't we way back just say that permutations commute with everything?
That is my point.
But isn't this one of the everything?
Yes. So
Can
this
you just say it's fine?
Yes.
Okay.
That is the punchline of this talk.
Okay.
The punchline of this talk is that the only way out of this, I claim, that's my argument, the only way out of this is just to accept equivariance as a primitive of the universe.
Oh, okay, great.
So if you don't believe in atoms, then you can't believe that equivariance is just true. And therefore you are condemned to prove it again and again and again.
I can just say that it's an axiom that is true and it's good.
Yes, that's right. And I wrote a 30-page paper that sums up to precisely that. That's exactly the point. Yes, Kieran.
Then I have to know then. So ZF or equivariant ZFA is ZF plus an atom, an axiom for atoms plus an axiom for equivariance. Can you build a model in ZF, or do you necessarily need to add these axioms? What's the relative strength in terms of like inaccessible cardinals and stuff that you need to start building?
So to answer your questions in order, yes, you can build a model. The model is dead simple. Let's do it in stages. First of all, EZFA is equivariant ZFA is the same thing as ZFA because equivariance is admissible in ZFA already.
Yeah.
So you can build it's the simplest equiconsistency proof ever. You just take your model of ZFA, it's already a model of EZFA. And ZFA is equiconsistent with ZF. Childishly easy, just start from the natural numbers and build up.
Yeah. Oh, so you only have a countably infinite set of atoms.
For today.
Okay, cool. Proper glatter isn't hard though.
I personally like to have a set of atoms, but yes, obviously, if you want a lot of atoms, then you have to accept the consistency strength of that lot of atoms. But there's no tricks to that. Thank you. Any more questions? Okay, so just to sum up, what I'm observing is that although it looks like we've made progress with all of this fancy schmancy nominal stuff and blah, 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 we've made no progress, really, deep down. Right? Philip is shaking his head here. Bear with me, bear with me.
I don't see how this squares with what John was talking about 2 hours back.
So
your claim, I mean. Right? That there's no escape.
Can we come back to that? Remind me at the end of the talk.
It's the end of the talk.
Oh God, nearly. We're nearly there. Now, equivariance. So basically, Marco has got to the punchline already that if we just accept this as a principle, then we're golden. If we don't, then we have 2 inductive proofs where we used to have 1. God has laid us a diabolical trap because equivariance proofs always succeed. It is always possible to prove equivariance. We know that this will always succeed. The problem is that the proofs don't scale. These equivariance proofs in practice, empirically, they swamp us. And I've experienced this myself personally. I tried to build nominal Isabel and I said, well, equivariance, we can just prove that on a case-by-case basis. Yes, we can, but not on human timescales. Now, I'm going to make a series of claims here. First of all, I'm going to claim that this isn't the fault of nominal techniques. Nominal techniques are exposing something deep about the mathematics. Nominal techniques are good at talking about names and bindings, so we can see it particularly clearly here. But I say if you're dealing with binding of any kind, nominal or not, wherever you are, then equivariance will be there somewhere, whether or not you can see it, and it is waiting to jump out and get you. That's not a mathematical proof, it's an assertion based on empirical experience. So I now believe that the true monster, I misunderstood my own PhD thesis. I always thought it was about freshness and atoms abstraction. Then I was pleased when I did nominal algebra, yeah, but actually the real problem is equivariance. Now, this is really unwelcome news. So there are various ways of dealing with bad news. One is denial. I don't have this problem. What problem? Fine. Enjoy the rest of your life. Anger. Had a lot of reviews. Gabbay's work is fine, but he doesn't explain the connection to blah, blah, blah. And that's an anger response. Bargaining. Let's get round this. You know, we can work something out. Let's fold in the meta language and ask the user to provide these renders, and we'll find a way around this. It'll work out. It will not. Again, this is not a mathematical proof. I'm just telling you the way I see it. You can't bargain your way around this one. You don't believe me? Fine. Enjoy yourself. Depression, give up, write papers about something else. I've been there. Acceptance. Okay? This is a real issue. Equivariance is there. How will we deal with it? It's actually not hard at all. You just have to acknowledge that atoms are a thing. You have to believe in atoms. Atoms aren't 0 or 1. Atoms are their own thing. And you have to acknowledge that equivariance is an axiom. And this is hard to do because for any concrete instance, you can prove it. But as Marco observed, you don't want to get tangled up in these nested inductive proofs. So I make the argument in detail in the paper, but I basically say, in principle, you could always get equivariance, but in practice, in order to get on with your life, you just have to say, it's an axiom. And then you can make progress. And that's what gets you out of that nested loop. So we have a slogan, atoms are real and equivariance is an axiom. That's what I meant when I said that I believe in atoms. And that was the hard bit. Now, I just want to spend a few minutes, and then I'll stop, talking about why this is hard. Please bear with me. Hands up who've seen the ZFC cumulative hierarchy. It starts from the empty set and goes upwards. Do you see any atoms in that thing? I don't. How about simple types? Who's seen simple types? You start from what? Natural numbers, maybe bool, and build functions. Do you see any atoms in this thing? I do not. No theorem prover or programming language offers atoms and equivariant permutations as polymorphic primitives. They offer functions.
Eustace's did.
Well, I overstate, except for FreshML, obviously. So perhaps we should talk about that. No non-nominal influenced programming language. Yes, I should refine that.
But that is circular, sort of. No non-nominal influence. Yes, obviously.
No, it's different. It's different because it's not as tautological as that, because nominal also suggests things like atoms abstractions, and it suggests you're coming from a certain approach. But I know of no instance. No, when they were building Lisp, they didn't think of just chucking in permutable atoms. Why would they? But there's no technical barrier to doing this. It's not a technical obstacle. So, we have been educated in a universe that assumes that atoms are not primitive. We saw that today when somebody, Kieran said, well, what if A is equal to 0 or A equals 1? There's a background assumption here that atoms aren't just atoms. And I claim this is an error. This is an opinion, right? This is a mistake. I want to point out, proving theorems is hard, but accepting that reality is not as we expected is much harder. The difficulty with names and binding is not mathematical. That's not the real problem here. It's a social problem. There's no problem with names and binding if you believe in names and binding. And I make formal what that is. It's EZFAC. If you believe in that, then names and binding are not a problem. But what that does is it puts atoms and equivariant permutations, it gives them equal status with other things that we take for granted, like numbers and functions. Okay, I can stop there or I can read this last slide. Who wants me to do the last slide?
I want to remind you about the question.
Okay, sure, go for it.
Well,
I want to read the last slide whilst...
Sure, good point.
Well, the question was, I don't see atoms in John's presentation, and it claims to give us substitution.
So as I liked that John was tends to point out that these are solving different problems. So yes, there is something that is identifiably a substitution, but that's not a solution, not to me, obviously, a solution to names and binding.
Why not?
Well, okay.
And let me be clear. I'm saying this as someone who's used functorial approaches to binding and formalizing a lot of stuff. So, you know, in practice, I can prove inductive stuff and, you know, theorems by induction on syntax in a setting that is a version, you know, syntactified version of what John was talking. I think, as I understand it.
So I certainly wouldn't want to diss what you've done and what Plotkin and Fury have done. But one thing you might, this is part of the reason that I gave the example of axiomatizing first order logic and substitution, because these are not syntactic. So I would be more convinced if you could show me how what you're doing produces a universal algebra framework with names and binding.
Okay, let's take it offline.
But I'll mention something else, putting the same point in a different way. You can look at the Haskell library that I built. So that's a real thing that you can play with. You look at how that's constructed. It's based on names, atoms, and permutations, and that's what I mean by names and binding. I suspect that what may be going on here, just as John said, is a confusion because we may be solving slightly different problems.
I think not, but okay, let's take it offline.
Thank you, Philip.
So I have a comment or maybe a challenge. If you could go to the slide where you mentioned no built-in system has a set of atoms, that might be helpful.
Excepting yours. Sorry.
Well, it's not that well known, so I don't blame you for not knowing about it. Okay, so you say you believe in these set of atoms, but in practice you always want to, you often want to have several distinct sources of atoms.
Yes.
And if you're working in a real system, you then also want to do meta operations on syntax where you say, oh, you give me some sources of variables and I transform your syntax somehow. So you end up having to have maybe several sets of atoms, and you need to say somehow that these are distinct. So you're giving me two distinct sources of variables.
I misspoke, or rather during this talk, I spoke as a set theorist. For example, in the Haskell package, which I built, I did exactly that. You declare an atom type, and there's there are polymorphic operations for manipulating types that are known to be atoms types. And in the set theory, it's not a problem at all. You just have to believe in more sets of atoms.
So yeah, I was just about to say, like, so I have lots of different kinds of atoms in my set theory, but none of them are equivariant in any way. But more that they help with doing other stuff and removing some proof obligations elsewhere. So there seems to be a similar theme of injecting atoms into systems to help you get away from problems that you never wanted. In some sense, like you've added some belief to get rid of some work that you have to do.
Yes. So there's a general principle, I'd go further. There's a general principle of using symmetry of some kind to save work. And what can happen very generally is that you build something and then you find yourself having to prove loads of stuff about particularities of how you built it that you never really cared about. And a standard way to deal with that is to parameterize over the symmetries that you find yourself having to eliminate. And this whole talk is an instance of that kind of thing.
And finally, do you have any more complicated types of atoms that have some more structure other than just being distinguishable?
Yeah, it's a wonderful question, Kieran. I don't, but there is a Polish school of nominal techniques. I can link you to their work. They're extremely smart and they're interested in things that they call atoms.
Yeah.
But the symmetries are different. For example, it might be atoms have the order type of the rationals or the reals.
Yeah, exactly.
Yeah. So that also works. It's not what this talk is about, but it's perfectly legitimate. Thank you. More questions?
Can you hear me?
Yes, I can. Hello, voice in a box.
Yes. Hello, Jamie. It's me. Yeah. So just to make sure I understand this correctly, you said to define inductive functions, you need the equivariance.
I'll go back to the slide. So
yeah, you try to define this function f inductively, but to define it, you need to have the equivariance.
Yeah, so we're trying to define this. And that breaks down into these three things, and this thing breaks down into that, and that forms an equivariance proof obligation. Yes.
Yeah, I'm a bit confused because, as you know, I'm also working on binding stuff at the moment, and I don't need equivariance for defining functions so I define like the most general function, the recursor on the data type that avoids bound atoms or bound parameters.
I understand.
And then every function is
we had a chat, if I may interrupt, Jan. I remember your excellent talk, and I pressed you on this point, and I asked you, where do you get such and such a lemma from? And you said, oh, the user provides it. It's easy. There's only 3 lemmas. Right.
Yeah, I think this is a mistake. So to define functions, I don't need anything from the user. What I meant there was if you want to do rule induction on inductive definitions, not on inductive data types. For the inductive data type that binds variables, I don't need equivariance.
I claim that you do. You may not have realized it yet, but I shouldn't use this pulpit to say that. I'm very, very happy to go through your work in detail face to face, and we can look through it and see if equivariance is hiding.
Let's do that.
Thank you. Thank you very much, Jan. I'm delighted you asked that. Okay, any more questions? Thank you very much.